Welcome back to the course in Nuclear Medicine Physics. Today, we're looking at different types of radiation detectors. In particular, we'll look at the gas-filled detector. And it turns out that depending on the voltage that you operate this gas-filled detector at, there's different types of ways that you can detect radiation. We'll look at a few different types of gas-filled detectors, including ion chambers, proportional counters, and Geiger-Mueller counters. Anyways, enjoy.
Well, so now we're going to start talking about radiation detectors. So what we talked in the previous lecture is how do different charged particles or photons interact with matter. So now we're going to take advantage of those interactions. If we know what's happening, maybe we can build some devices and do some measurements to know when there's radiation or when there's no radiation. And that's the topic about radiation detectors. So let's see. So yeah, in the previous lecture, we saw that when radiation is traveling in matter, they can cause excitations. So either the molecules or the atoms, if it's just from one element, I move to an excited state, and then we can have some emissions coming out of those excitations when those molecules or atoms of the elements are coming down to the ground state again. Or we also have ionizations. And ionizations is when these particles remove electrons from the atoms. So now that atom that's left behind has a net electric charge because there's going to be more protons than electrons. Because this radiation causes ionizations, that's why an ionization is the main effect. That's why you typically hear the name of ionizing radiation. And ionizing radiation is the one that you typically hear being very bad because these ionizations, for example, can cause that's basically what's causing bad effects on the DNA of cells because ionizations then make free radicals that they end up combining with different things or damaging the DNA. So it's ionizing radiation, also a name for radiation that causes those ionizations. So what is that we want to know when we think of building detectors? So we want to see if maybe what we want to be able to detect radiation, of course, so is there radiation present? If there's radiation present, is there a way for us to quantify how much radiation is there? And if we know that there's radiation there, is there any way for me to know what are the energy of the emissions coming out of there? Is there a way for me to know, for example, if a particle is a beta particle, or if I'm measuring, or if the radiation that I'm seeing are photons or alpha particles? Yeah. So we have several groups of radiation detectors, and we are interested, well, for the particular case of nuclear medicine, we're interested in using the radiation to generate images, but then we also use detectors in the nuclear medicine, not in the nuclear medicine application itself, but in the nuclear medicine practice in the hospital. For example, we need to be careful with staff exposure to radiation, so we use detectors for radiation safety. And the processes of photon interaction with matter. Okay, so when we have photon interactions, we just need to keep in mind, remember, photons don't directly deposit energy in the medium. It's more like the electrons, but these photons are going to create free electrons in the medium, and then these free electrons are going to transfer their energy to the medium by that ionization and excitation. We have different types of detectors. We have what we call charge carriers, which typically are gas field detectors. We have semiconductors detectors in which we deal with electrons and holes. And we have what's called scintillator detectors, which are some detectors that emit light when there's interactions with radiation. Okay, let's start talking about gas field detectors. So what is a gas field detector? You can think about having a chamber that is filled with a gas. So imagine just a little device that has some gas inside. Now that gas can either be pressurized gas, or it can just be basically air. It's just exposed to the atmospheric pressure. We can put a different voltage between two electrodes. One is what we call the cathode, which is going to be the negatively charged electrode. And we have the anode. Wait, am I saying that right? No, the anode, yeah, the anode is going to be positively charged and the cathode is going to be negatively charged. And what you have then, when you put this anode and cathode, one is positive, one is negative, what you have there is that you generate an electric field. So there's this difference in voltage that causes an electric field. So when ionizing radiation goes through this chamber, well, again, because of the name, it causes some ionizations. So in this gas, we're going to have some positive and negative ions. So now we have these charges. So positive charges are going to move towards the negative, like pole of the battery, and negative charges are going to move to the positive side because, again, because of that electric field there. So positive charges travel to the cathode, which is negative. Negative charges travel to the anode, which is positive. And when we do this, when these charges are moving, what we can measure on the other side of the device is an electric pulse or an electric current. Okay, but then let's think about, okay, we can have this anode, this cathode. What's the voltage that we can put there? So we can start building a graph in which we're going to start increasing the voltage of that ionization chamber, that gas filled chamber. So if we start from 0 voltage, and then we start applying a little bit of a voltage and then start growing and growing, we see first this region that is called the recombination region. So what is a recombination region? Is that the particles that are traveling into this gas, they create ionizations, but the electric field is not that high. So these ions then recombine by itself before even reaching the anode or the cathode. And yeah, so they become neutral again. And well, as we start increasing the voltage, we get a higher amplitude of the pulse, but some of them at little voltages don't really make it to the other side. They don't give as much of an output pulse. But as we start growing, then it starts increasing and increasing the pulse. Then we get to a voltage that we call the saturation voltage. And this brings us to what we call the saturation region. So what this means is, although we keep increasing the voltage, we don't really see too much difference in the collection. Well, we don't really see a difference in the collection of the charge or in the collection of that pulse that we're able to measure. And the reason for this is that all the charges created inside the gas by that ionizing radiation is being collected. So we're basically collecting all the charges. No matter if you apply a little bit more voltage, you're still collecting all the charges that are generated. So that's why that output is not created. And this region, in which we call either the saturation region or the ion chamber region, is what brings me to the first type of detectors, what we call the ion chamber detectors. Now, most of these ion chambers use air as the gas. So as I said before, these chambers may be at a high pressure. So of course, if you have high pressure, that chamber has to be sealed, or it can be exposed to the atmosphere. So it's not sealed, it's just at atmospheric pressure. Now the voltage between the electrodes should be high enough that the ion pairs do not recombine with each other. So again, that recombination region, we now want to collect all the charges. We don't want some of them recombining itself and losing them in the process. So that voltage tends to be sometime in the order between 50 to 300 volts, depending on the particular design of the chamber. Well, yeah, if we're talking about a gas, the typically amount of charge released in an ionization event from an ion chamber is small. It's in the order of 34 electron volts per ionization event. So basically you need about 34 electron volts to create one ionization event. When you think about a 1 MeV beta particle, that releases a total charge of approximately 10 to the negative 15 coulombs. So in total, we collect the total charge, total ions of 10 to the minus 15 coulombs. Ion chambers then are not really used to measure individual radiation events because the collection is just very small. So what we measure is just the total current produced by that beam of radiation. So we just collect the height of the pulse on the other side. Well, not on the other side, but on our measuring device. Yeah, so you can either measure the current, or you can see how many charges you collected. Now, ion chambers are typically used in what we call survey meters. These are just two photos of how survey meters can look like. So, well, to be able to measure that current, now instead of me saying in the other side, what's typically being done is we use a device that is called an electrometer. So electrometer, we plug it into our chamber, and now we're able to collect either a charge or measure our current. Because of the low voltage, again, I said only at the ionization events caused by that initial but that radiation that is hitting the chamber is collected. And what I mean with this, and we're going to say this in a moment, is this voltage will create ions, but those ions are not going to be energetic enough to create more ionizations. So we're only collecting the ions that come directly from the interaction of that radiation with our gas chamber. The newer units, so our typically current equipment, they are calibrated to read values in milligray per hour or gray per hour. Basically, it's a dose rate. Again, at some point in the course, we're going to understand much better what dose really means, but this is how much energy per unit mass gets deposited per hour. So we're measuring a dose rate. And they can typically read values from 10 microgray per hour up. Now, do we use these devices really to create images of a patient? Well, not really. They are just mostly used for radiation protection. If you want to detect if there's some radiation around or if there's some contamination. We have another device. We call this device a dose calibrator. So again, it's an ion chamber. Now, those calibrators, compared to other typical gas chambers, they are actually pressurized chambers. So the gas that's contained inside this chamber is typically argon. And yeah, actually, one of the reasons that those calibrators end up failing, they're very robust, but when they end up failing, there's a big chance that is because they start leaking this argon gas, so the pressure starts going down, and now they're not as efficient. Now, we calibrate this equipment to read units of activity. So what do I mean with that? We actually read megabecquerel or millicurie, for example. But to do this, if we want to measure activity, then we need to think on putting some calibration factors that are measured for different radioisotopes. Okay, let me keep going. So we use them to verify, for example, how much was the activity that was extracted from a radionuclide generator. So we go on to inject technetium-99m to a patient. It comes from molybdenum, the generator. We elute it, but then we need to know, okay, how much is there? And then if we know how much activity comes from the generator, then either we can also prepare our injections, and then we see, okay, how much activity am I actually injecting into a patient? Or if we are dealing with a radiopharmacy and the radiopharmacy is preparing samples, then they need to ship those samples to different hospitals or different places around the world. They need to know how much activity are they shipping. And there's all regulations for shipments. There's, of course, radiation safety involved on what type of injection is safe for a patient. If you inject too much, then you end up getting some radiation toxicity. If you inject too little, then you maybe won't be able to collect any images because it's just not going to be any useful information there. So this is important. Now, these values, the values that we measure in a dose calibrator, are typically in the order of the megabecquerel range, because well, those activity values might be too large to assay with maybe other types of detectors, like for example, the ion chambers that I started talking with. Um, okay, so when we put a sample inside the dose calibrator, and we're going to look at it a little bit more in detail in the next lecture. Well, you cannot really isolate or filter the energy emissions. So dose calibrator is just gonna detect all the different particles coming out from the radioisotope. So they're gonna measure all the amounts of ionization charges that this sample produces. And well, and then we need to make some corrections for it. So what you think is then we put a sample in the dose calibrator. What this sample is doing is it's giving us a current. And what we're trying to calibrate is, okay, for this amount of current, how much is the activity for this radioisotope? And we have to do this for all the different radioisotopes that are being used in the clinic because things that can happen, because isotopes have different emissions and different energies, what can happen is that the same amount of activity from one isotope, if you have two different isotopes with the same amount of activity, they can generate different, well, they can give you a different pulse current in the reading because, again, the different emission areas. So that's what we need to put a known activity, a standard activity, a standardized activity of a particular isotope, and we have to do what is called a calibration curve of, okay, this amount of current for this isotope in particular represents this activity value. Now for this other isotope, this amount of current represents this activity, and so on and so on. And we do this for many different isotopes. And then if you don't have the isotope, there's a way of interpolating the curve, but well, we're not gonna get into those details right now. Now, another thing you can think is, well, because of the geometry of this chamber, we can think that if we put too much volume or too little volume, it might affect the number of ionizations that you get for a same amount of activity. So we do several corrections. We correct volumes by doing what we call the geometry test, and the linearity. Well, there should be another bullet out here, and we also need to know that because of the way that we're converting current to activity, we're making it linear, basically. We're saying, okay, I have this current, I multiply by this factor, it gives me some activity. But is that factor going to be the same if you're measuring 1 megabecquerel or if you're measuring 100 gigabecquerel, for example? If it's going to be the same calibration factor through a big range of different activities. So that's what we call a linearity test. And these are some examples of things that I've done, for example, in our clinic. This is how a geometry test typically looks. So we perform geometry tests for different sizes of syringes. So again, we go from 1 milliliter syringes all the way to 10 milliliter syringes. Those are the ones that we typically, all the range is what we typically use when we inject patients. So we just need to make sure that as we start increasing the volume, our activities are accurately measured. And one way of doing that is that first you put a little bit of activity in the syringe and you measure it. And then instead of putting more activity, you put a little bit of saline or a little bit of water and you measure it again, and then you put more water. So the activity is supposed to be constant throughout your measurement, but you are increasing the volume. And we look to be within 5% all the time of the initial value. And we do that process for different syringes. And it's a way of checking our quality of our dose calibrator. We just make sure. Now, if you see differences, then it doesn't mean that your dose calibrator is bad. It just means that you need to account and create another correction factor for different types of geometries that you use, so that you know, okay, if I use this geometry, I know that the reading doesn't correspond exactly to what I'm supposed to be having. I need to multiply my reading for another, do another correction to finally get my true value. And then linearity is what I was saying, because of this conversion throughout a big range of activities, we just need to ensure that that's the case. So one of the ways we do this is we take a sample of a high activity, and we leave it in the dose calibrator, or we take measurements of this sample at different at different times throughout its decay. And well, in principle, that decay should follow the decay that you expect. So we know the half-lives of the different isotopes. So is this actually following that half-life? And well, in this particular case that I'm showing here, yeah, this is a logarithmic plot, so it follows a line. We see that the predicted activity based on what we know of the physical decay and the measured activity is corresponding. And yeah, so there's a very, very little variation in linearity. So then we know that is accurate. So, well, this is how an ion chamber for the dose calibrator looks. So you have the cathode out here, the anode is right in here, you have the argon gas inside. So you put your sample inside the dose calibrator. So here is represented by the syringe, or you can put a vial. So look at, those are two different geometries that might cause slightly different number of ionizations. This causes a current when the gas is ionized that the electrometer and the electronics in this device measure, and we multiply that current by that calibration factor, and then we can, at the end, measure our activity. Another type of ion chamber, and again, this one is for radiation protection, is something that we call pocket dosimeters. And pocket dosimeters look like this. So the way, okay, so pocket dosimeters are used to measure, to monitor the radiation levels at which staff are being exposed. So how does it work? So it's basically a capacitor, so in a gas. So you have this capacitor charged. And so you connect these pocket dosimeters into a device that charges this capacitor. But because this capacitor is inside an ion chamber, what's going to happen? Well, it's inside some gas. If ionizing radiation comes into the dosimeter, it's going to cause some ionizations. And then positive charges are going to go to the negative charge plate of that capacitor, and negative charges are going to go to the positively charged plate of that capacitor. And as this goes on over time, you start discharging that capacitor. Now, this device has a little dial, so you can, okay, so there's a little window here where you can look with your eyes, and there's a little dial inside that's pointing you. So that dial is calibrated to that charge of the capacitor. So as the capacitor is discharged, that little dial moves, and you can, well, there's a scale calibrated to represent the dose in that staff member has received. Then once the capacitor is fully discharged, you can again connect this little dosimeter to a device that charges the capacitor again, and then you can reuse it. Yeah, so that's basically what I just said. Now, there are some limitations for the ion chambers. One is that they are very inefficient as detectors for X-rays and gamma rays. And well, in a way, yeah, gamma rays and X-rays are more or less high energy photons. So coming back to our attenuation coefficients, then because these gases are not very dense, then the probability of interaction of these X-rays and gamma rays is small. So only a small fraction of those photons traveling in the gas will actually interact. And now the response is also changed with photon energy. And what you can think, okay, now these chambers have a wall. So depending on the energy of the photons, maybe you end up getting some ionizations caused by actually interactions from the photons on the wall, not really necessarily on the gas, but then that changes as well with the energy of the photons. This is not a big limitation for pocket dosimeters or cybermeters or dose calibrators, however, but it's of course not good for imaging applications in nuclear medicine, because to be able to create a good image, we need to be able to detect a big number of gamma rays or X-rays. There's another limitation. So if you are using unsealed chambers, those are the ones that are exposed to atmospheric pressures, then there might be differences in absorption efficiencies if, for example, you are at sea level compared if you go up a mountain. And then there's differences in that pressure if you're at 22 degrees Celsius, which would be room temperature, if you are at 40 degrees Celsius. So these chambers are calibrated for sea level and room temperature, but if you are doing your measurements in different conditions, then there has to be one calibration factor that also needs to be taken into account. That is typically calculated by taking the reference pressure, which will be this one, divided by the pressure at which you are taking the measurement times the temperature at which you are taking the measurement over the reference temperature, which is 22 degrees Celsius. I'm going to edit this slide just to make it explicit that this is Pref and Tref, because now I'm seeing that there might be a confusion there. So that's ion chambers. Now I think there's some people asking why they put argon, not other type of noble gas. For me, it's hard to ionize argon. I'm only using argon. Armand, do you know why they would use argon instead of another noble gas?
Yeah, what is specific about argon?
So they use a noble gas just because, of course, you want this argon to remain being argon for as long as possible. But I don't really know exactly why would argon be the gas to choose. So I'll do some investigation about that and I'll get back to you. Okay, so let's keep increasing the voltage. Now we are in the ion chamber region. We can keep increasing the voltage. And then we get to a region that we call the proportional counter region. So what this is happening is as you increase the voltage, your output pulse starts going higher and higher. So, well, although you would think that they might be just ionization chambers that operate at higher voltages, not really necessarily the case. They're actually designed to optimize what we call the gas amplification. Oh, sorry, I skipped one slide. Yeah, so when the voltage of the ionization base increase, okay, if we now increase this voltage, what happens is that these ionizations that are caused by the radiation, then these particles have enough energy to cause extra ionizations when they collide with other particles of the gas. And these additional ionizations is what causes what is known as the gas amplification. And then you can think about defining a factor, which is the gas amplification factor. That is the factor by which that amplification is increased. And then typically in proportional counters, it goes from 10 to the 3 to 10 to the 6. It grows and grows as the voltage is increasing. So if in the ion chamber you had one ionization, maybe in this proportional counter, that one ionization is going to become 1,000 ionizations. So you don't measure the total amount of the initial charge. You now measure that total charge after the amplification. But what I was saying, I'm going to go, they are not really just ionization chambers that are operated at high voltage. They are actually designed to optimize that gas amplification. And they typically use noble gases or mixtures. So one example is argon 90% and methane 10% would be a combination that would be useful. Now, this pulse is, of course, higher than the just an ionization chamber and is proportional to the amount of energy deposited in the detector. So it's very useful if you want to discriminate different energies and types, because you bring your detector, you have a height of your pulse. When, let's say, you have a small height, a small amplitude pulse, if that energy is low, you get a higher amplitude pulse if your energy is higher. So you are able to distinguish more or less when you have already low energy radiation and when you have high energy radiation. And it's also useful for detect and just count individual radiation events. They are still, however, not very sensitive for X-rays or gamma rays. So again, they're not very useful for nuclear medicine, besides probably just radiation protection in the clinical environment. They're mostly used to measure non-penetrating radiation, such as alphas or betas. And we haven't fully talked about these. We're gonna get that to it later, but Alpha particles and beta particles can be easily stopped with a very thin piece of paper, for example. So that's what we mean that this is non-penetrating radiation. So if it's outside of your body, well, it's hard for it to enter your body unless maybe you just swallow it or something like that. When we have large area gas proportional counters, they are typically used to measure surface contamination when typically that contamination is caused by alpha, beta, or gamma isotopes. Okay, and then let's keep increasing the voltage to that gas chamber. So you start increasing to the proportional counter, you start going up, you keep going up, you keep going up. But then you get to this region that is more or less flat. It's not exactly horizontal. It has a little bit of a slope, but it's not a big slope. And this is what we call the Geiger-Mueller region. So what is that Geiger-Mueller region? So Geiger-Mueller counters, which is the name of these detectors operating in this region, are called. This is a region that is typically between 500 and 900 volts between the electrodes. And they're designed to have the maximum gas amplification as possible. So remember, before we were in that proportional region, we had an amplification between 10 to the 3 and 10 to the 6. Now in Geiger-Mueller counters, it will typically go up to 10 to the 10, a factor of 10 to the 10 of amplification. Geiger-Mueller counters are sealed, and again, typically filled with argon. Now, these proportional counters have this gas amplification, but then the issue is that gas molecules can also become excited. And if these molecules are excited, then when these molecules come down to their ground state, we have an issue, and is that they typically emit ultraviolet light. And if you have this ultraviolet light, then what this causes is that maybe this ultraviolet light is going to cause some other ionizations by itself. And then this is just resulting more and more avalanches. And avalanches, you receive one particle and this amplifies. And you receive one particle that just gets amplified and amplified in different ionizations. So because there's this UV light that can cause more ionizations, and then this is just resulting in more avalanches, and then this just can be up to a state where it just can keep going. We need to stop those avalanches caused by this UV light. And to do that, we use what is called quenching gases. So quenching gases basically will stop the avalanches. So quenching gases can be, well, common quenching gas can be alcohol or chlorine are typically used. So what are they doing? One, these quenching gases give electrons that neutralize the positive ions. So you have an ionization, you have positive ions, you get negative ions. The negative ions will move much faster towards the positive charge of the electrodes. The positive ions are heavier, so they move slowly. So in that process of moving these positive charges, these quenching gases will share some of their electrons, so then that positive charge is going to be neutral again. Now, these quenching gases, if the molecules of the quenching gases are excited, one of the things that is very good about it is that they are not going to come back to the ground state emitting UV light. They will instead kind of create molecular fragments. They're going to fragment themselves. And a third characteristic is that these quenching gases strongly absorb UV light. So then this UV light, instead of causing more ionizations, is just going to be completely absorbed by the quenching gases, and that's going to stop the avalanche. Let me just see something. Okay. Now, okay, I'm going to say it here because I don't know if I have it. Typically, when organic gases are used, for example, alcohol, what happens is when they have these molecular fragments, they can just fragment, and then those molecules are not going to become what they were before. So as time goes by, then you are going to start losing your quenching gas. So after a while, it needs to be replaced. But when chlorine 2 is used, chlorine use these molecular fragments actually recombine into chlorine molecules. So then these detectors will last for much longer. After they disintegrate those molecular fragments, they can come back together. Now, on Geiger-Mueller counters, the current that you measure does not depend on the deposited charge. So it cannot be used to distinguish different energies. Here you detect two different events from two different energies. They're just gonna create an avalanche, and what you're gonna measure is just an avalanche. You're not gonna be, as in the proportional counters, that pulse is not gonna be different depending on the energy. So Geiger-Mueller counters are very useful for detecting and counting individual radiation events. You can count, that's why they're called Geiger-Mueller counters. You'll know if you had one event or three events coming. They're mostly used, again, in radiation protection for detecting the presence of radiation. Still not very useful for nuclear medicine purposes, because again, they're not very sensitive for X-rays or gamma rays. Geiger-Mueller counters are also used in survey meters. So they are survey meters that are approximately 10 times more sensitive than the survey meters that work in just the ionization chamber region. Changing the thing, okay, so if you look at this device that I'm showing on the right, and this is what we call typically a pancake and device just because of the shape that you have in the detector. Well, if you change the thickness of the entrance window, you can identify a little bit the energy of the radiation. And well, because thicker, I mean, low energy radiation will probably not be able to travel through a very, very thick window. And something that it's used to, for example, distinguish gammas from, if you have some contamination and you want to know if that contamination is caused by a beta emitting isotope or by a gamma emitting isotope, one of the ways that is done is, because betas are easily stoppable, you put like a little plastic on this entrance window, and if you don't measure anything, but then when you take the window, you have some measurements, you know that those are caused by betas. It's just that the plastic is stopping your betas. Gammas, well, the plastic is basically transparent to the gamma. So if you put the plastic window and you still see exactly the same as when you didn't have the plastic window, you will know that that contamination that you have there is caused by a gamma emitting isotope. Yeah, so that's how it's useful to identify between penetrating and non-penetrating radiation. Are there any questions up to this point? Well, scintillation detectors, I'm not gonna go into details. I just want you to know that it exists. Armand is gonna give a very, very nice lecture of this, and we're gonna start looking into some mathematical measurements that we can do with this. But just as a quick introduction, these are just some detectors that when they interact with radiation, they emit some light. And scintillators can be plastic, can be organic or inorganic crystals. We can have liquids or we can have gases. Liquid scintillators, for example, what I'm showing here in the left, they're typically used for beta particle detection. You mix the radiation with your liquid scintillator, and then they emit light. So that organic solvent will dissolve the scintillator in a radioactive sample, and then we can place this solution into a detector to just count the light, and we'll be able to quantify this. And well, it's just so you know, but stay tuned. The next lecture is focusing more on scintillators. And lastly, let's talk a little bit about kind of newer technologies, which are semiconductor detectors. Semiconductor detectors, you can think, is similar to the gas detectors that we just talked about, but in the solid state world. So now think about, okay, when you had a gas and we said, well, the gas is definitely not dense enough to really stop all the gammas. Now this is solid, this is in the solid state. These are solid detectors. So they have a magnitude of around 3 times higher. So they are 3 orders of magnitude denser than gases. So if they are denser than gases, they can produce ionizations for 10 times less energy. So the electric signal that you can measure becomes basically 10 times higher than in gas detectors. So now they start becoming more efficient for X-rays and gammas, which was the limitation from all those gas detectors that we discussed a moment ago. Now, the signal from these detectors, they do allow for the detection of individual events, and the amount of the signal that we collect, so that pulse of energy, is proportional to the energy absorbed. So if there's a higher energy photon or a lower energy photon, we'll see a difference in the electric pulse that it generates. So we started looking, okay, these are typical materials of semiconductor detectors. So some semiconductor detectors are made of germanium, some others are made of silicon, and they're very, well, they're very good. It's just that they have a very big limitation, and it's just that they require liquid nitrogen temperatures to operate. The reason for this is that at thermal, okay, at room temperature, basically, they do conduct electrical currents. So then that adds noise to, well, there's background noise in your current. So you don't want to use that noise. It just contaminates your measurements. Now, when we think about germanium and silicon by itself, they can end up having some impurities. And when you have some impurities in these solid state detectors, these impurities create what is called an electron trap. So if you have an ionization event, and this ionization event removes electrons from some atoms, instead of us being able to measure that electron with an electrometer, this contamination inside the crystal, well, in the lattice of these crystals, end up trapping those electrons, and then we don't see it. So this makes us lose energy, lose some of those electrons that we should be collecting. So to solve those problems of those impurities, people have tried to then maybe create a very, very high purity crystal. And that's what HPGE stands here. So this will be high purity germanium. So if that germanium is very, very, very pure, then we would be able to reduce the effect of those impurities causing those electron traps. However, doing a high purity germanium crystal is very, very expensive. So, well, it's expensive. It's being used though, but it's expensive. So another option to deal with those impurities in the crystal that are taking some of our electrons is by introducing impurities that do the opposite. Those impurities will donate electrons. And that's why, for example, we have lithium. So that's why you have here germanium with some lithium, silicon with some lithium. So we're in a way trying to compensate for those impurities by adding lithium. And what lithium is going to do is that it's going to give us some electrons to compensate for those electrons that those traps will be losing. Silicon, okay, yeah. Germanium detectors have very, very good energy resolution. We're going to see a little bit graph in a moment. Silicon are typically used for alpha, beta, and very low energy gamma detection. So they have good energy resolution, but they also require very low temperatures to operate. Now, germanium, they have an even higher limitation, is that they don't only really require liquid nitrogen to operate, they also require to be stored at very, very low temperatures, or your detector is just gonna damage. Silicon, you can still store it at low temperature. Sorry, you can still store it at room temperature, but if you want to make the most of it, it should still be stored at very, very low temperatures. Now, in recent years, to address these issues, people found out these new type of detectors, which are called cadmium zinc telluride. Well, we just refer to them as CZT. And the main advantage of these detectors, again, they're solid state detectors, but is that they don't really require cooling. They are very efficient. Okay, so they can operate very well at room temperature, and that's a very, very big advantage. And they can be made into small arrays of detectors, into arrays of very small detectors. So it's really hard to make a very big crystal of CZT, but they found applications when arrays of small detectors can be used. They have excellent spatial and good energy resolution, but we'll look into those details as we keep going. Okay, so yeah, so the introduction, either the growing of high germanium detectors or the introduction of those impurities for those crystals to compensate for the electron traps is very expensive though, and it's very time consuming. Crystal sizes, we cannot make them very big. They're small, typically 5 centimeter diameter would be typical for a germanium detector, or a silicon detector will probably won't be able to be made more than 1 centimeter thick. And the other thing is lithium, and that's why I was saying about lithium condenses at room temperature. So yeah, that's the reason why those germanium doped with lithium detectors need to be stored at very, very low temperatures, because otherwise this lithium just condenses and it will just damage your detectors. High purity germanium, though, is what's become the gold standard for gamma spectroscopy. So what is gamma spectroscopy? Gamma spectroscopy is when we have a sample and we want to see what are all the energy emissions for all the energies of all those gammas that are being emitted by a sample. So you can do a graph of different energies and how many photons of each energy you have, because of the high resolution of germanium is very, very used in these applications. And silicon is typically used in spectroscopy of low energy X-rays and beta particles. Again, similar when we want to measure the energies of a sample of different betas and X-rays with low energies. CCT detectors, as we saw, can be operated at room temperatures, and because they have such a high Z, this increases the sensitivity to gammas. Even if they are thin detectors, even if they are thin detectors, we can still measure a lot of the gammas. However, again, as I said before, it's very hard to grow big crystals of this material. So it has found applications in nuclear medicine, but only when we can use small detectors or an array of small detectors. Now, they're still expensive. Even making this array of small detectors becomes very expensive. So it's starting to make it into the clinic. There has been some cameras typically used to image the heart that are becoming more and more popular. But I can think that as technology keeps advancing, hopefully they get more and more popular. And one of the reasons, again, I'm only going to show this more in detail, but if you compare, for example, a solid state detector like what we see on the left and a sodium iodine detector, which we see on the right, which is a scintillator, and you want to measure energies of photons, in this case, it will be the sodium 24 spectrum. Look at, for example, this energy, 2.75 MeV. This sodium detector gives you a very, very wide peak compared to the solid state detector. So yeah, so semiconductor detectors are very good at narrowing. Basically, this is something that we call energy resolution, and we're going to get into more details about what energy resolution means, but is that energy resolution in this particular case that makes it so good for gamma spectroscopy compared to other types of detectors.
If I may,
yeah.
Carlos, if I may just add a comment. Yeah, in later chapters and discussions, lectures, we will see, especially when we talk about some new exciting state-of-the-art SPECT imaging devices, that there's a lot of action happening on CZT or CZT. So you know, stay tuned, because we're going to talk more about some specific examples of that. But you're going to keep hearing about this, and even though we're going to talk about scintillation detectors, which have been the primary sort of approach to detection of gamma rays in detail, we're going to talk about those. But again, semiconductor detectors are definitely starting to appear in newer applications.
Maybe I just realized, but you can think that how is that these detectors look? So you would have something like your solid state material here, and then you have like an electrode that you connect to the positive side, and one that you can connect to the negative side. So when ionizing radiation comes into these crystals, that's when they create negative charges moving to the right and positive charges moving to the left. So we measure that current, and that's how we're able to know, depending on the pulses that we get, we know the different energies. And yeah, but it's similar to a gas field detector. It's just that this, it's just in between the electrodes, instead of having a gas, now you have this solid state material. Now, other types of detectors, and not necessarily used in nuclear medicine, but it's just detectors that are used to measure different types of radiation. There's something called multi-wire chambers. So there are parallel wires in a gas volume. And these are typically used because according to which wire produces a signal, so you have a gas, but then it detects exactly in which of those wires, something like as you look in the right, depending on which wire receives the signal, then it's possible to track the trajectory that a particle is following inside that detector. There's also scintillation fibers, which are arrays of scintillators that they give you good spatial resolution, but it's really hard to read the signal. There are also detectors to measure Cherenkov radiation. There are some other detectors called time projection chambers, and a place where you can combine everything and all the types of detectors that I guess has been out there is, for example, at CERN, at the Hadron Collider, where people are just working on detecting all types of particles of charged, non-charged, and trying to look into understanding fundamental questions of physics. So what makes one radiation detector better than another? And again, stay tuned. We're gonna talk and we're gonna look at the math of each of these different bullets that I'm putting here. Is your detector efficient, or is the sensitivity of that detector high? So that basically means how many photons from the total number of photons are you actually, or how many particles from that total number of particles that are there are you actually detecting? How can they handle a counter? That means, can they measure a lot of photons hitting it per unit time, or they can only measure if the number of photons reaching it is not that high? Can we distinguish one photon from one energy well from a photon from another energy, or is just a big overlap? We don't really distinguish the energy. Do they have good spatial resolution? Are those detectors good to tell us where that radiation event came from? And what's the time resolution? Do we know exactly when that particle came to our detector? I have some slides here of something that is called the silicon photomultiplier, but I think I'm gonna leave it here. Armand is gonna teach us about scintillators, and he's gonna talk a little bit about something called photomultiplier tubes. So when we look at that, let's come back here and see the new technology of photomultiplier tubes. So you have the slides.